Welcome back to part 2 of chapter 5, Applying Newton's Laws. All right, so far we've been flat. Now we are going to go on an incline or a ramp, an uphill or downhill surface. So when we are analyzing forces on an incline, there are a few things to keep in mind. First, weight always goes straight down. So here I have my weight, and my weight force is going to go directly straight vertically down. The normal force, however, remember, is normal for perpendicular. Perpendicular, or normal is the word for perpendicular in physics. So the normal force has to be at a right angle to the ground or to the incline. So the normal force is not going to go straight up. It's going to go off at an angle. If I know the angle that the ground is at, like right here, that angle there, that angle will be the same off of the, what we'll call the x-axis, right? What used to be the flat x-axis is the same as the angle that the weight is coming off of what used to be the y-axis. Actually, the weight is going straight down, but that's off of our new y-axis. When we tilt, we also are going to tilt our x-axis, so like that angle, right, between what used to be horizontal and our new x-axis. Our x-axis is now along the ground, and our y-axis is now tilted going up where the normal force would be. All right, so we tilt the x-axis, we tilt the y-axis, the weight goes straight down, and then we've got an angle. And that angle is the angle of the slope, so like a 20-degree slope, for example. Additionally, my weight, which is going straight down, I can break down into both horizontal x components and vertical y components. The vertical y component has to be matched by the force going up. So this normal force will match the y component of the weight in most cases if there's not another vertical force. So if there's like a tension force or something pulling it up or pushing it down, then it'll vary. But in many cases, that y component will be equal to the normal force. Okay, and pay attention to the negatives. It's going down, so that's a negative weight in the y direction. Couple mistakes to avoid. Number one, remember that the normal force goes perpendicular. It doesn't go straight up if you're on an incline, so not like that. Make sure it's perpendicular. And number two, make sure that the weight does go straight down. The weight does always point straight down. It doesn't follow your new y-axis. Okay, your weight always pushes down to the center of the earth. And the center of the earth doesn't care if you're on a hill or not, because it is not conscious. The center of the earth is a big ball of iron, we think. We haven't actually been there, but that's what the evidence points to. Let's take a look at a stop and think. A mountain biker is climbing a steep 20-degree slope at a constant speed. The cyclist and bike have a combined weight of 800 newtons. Referring to figure 5.11 for guidance, what can you say about the magnitude of the normal force of the ground on the bike? Okay. So I know that the weight is 800 newtons. I'm actually going to start by drawing my force diagram here. I've got my biker there. I know that the weight goes straight down like that, and the weight equals 800 newtons. I know that my normal force goes perpendicular to my slope like that, and that is going to be my normal force. Okay? And then the question is my normal force the same as my weight? Is it less than my weight? Is it more than my weight? And I've got a 20-degree angle that it's going up. Okay, so for me, this one really stumped me. I don't know why it really stumped me, but I had a tough time figuring this out. And the way that I could figure it out was by treating my weight as a vertical and a horizontal component. So there's my y component of weight. And then I also need to have an x component of weight, which would be like here. You could also draw it here, right? So I know that my weight is broken down into W sub y and W sub x. I don't know if that color is showing up, so I'll try it in green. There you go, W sub y and W sub x. Now, my normal force, I know that the cyclist is staying, like it's not sliding back down the slope, and he's not lifting off the ground and not falling into the ground. So if I take this normal force, this red arrow, and I transpose it, I'm going to make it blue, it should take me with the same exact shape right back to the surface of the earth, right? Back to the surface of the hill. Then, in order to make sure he's not sliding down the slope, I know that there has to be a third force that would be exactly that long, right? That long right there. And it's going to go up the hill, like there. Okay, so same length going up the hill. And that has to be the force of the ground on his bike tires, right? That's basically the force that he's putting in with his feet to keep himself going up the hill at that constant velocity. Because if he didn't do that, he would slide back down the hill, and riding your bike backwards downhill is very difficult. Do not recommend. And that one would have to be equivalent to the weight X component, right? It would actually be the friction force, but it's an X component of weight. So that means I've got the X component of weight that's balanced out by the X component of weight down here, right? These two balance each other out. And then the normal force has to be balanced out by the vertical part, the Y component of the weight. Since there's an X component of the weight, right, I know that this leg of the triangle is not going to be as large as the full-on weight. The full-on weight is going to be the biggest one. So the normal force will have to be less than the weight. It'll be equivalent to the Y component of the weight, not equivalent to the entire weight. So that leaves me with C less than 800 newtons, okay, by breaking it down into its X and Y components. All right, let's talk a little bit about friction. So for friction, there are three types of friction. There is static friction over here. The static friction is equal to the force that I am pushing on the object, but not making it move. So if I have an object sitting in place and I'm pushing on it, but it's not moving, then the force of my push is equal to the force of static friction pushing back against me, because I'm not making it go anywhere. Those forces are equal and opposite, and it's keeping it in place. However, at some point, I could push hard enough to move that heavy object or light object. And at that, I would call the force of static friction maximum. So the maximum static friction force, as hard as I push it right before it moves, would be equivalent to the coefficient of static friction times the normal force. So the normal force is the floor pushing up on it times the coefficient of friction, and that'll give you its static friction maximum. I can also find the kinetic friction force, which is the coefficient of kinetic friction times the normal force, and I can find the rolling friction force, which is the coefficient of rolling friction times the normal force. You'll notice that all three of these are very similar. They're the normal force times the coefficient of friction. So the friction force, coefficient of friction, times the normal force. So what are these three different types of forces? Static friction keeps it in place. Kinetic friction is if it is moving, sliding across a surface, how much force is required to keep it moving at any speed. And the rolling friction force is how much friction is required to overcome the rolling force. And you'll notice in terms of magnitude, the static friction force is the greatest. It takes the most force to get something moving in the first place. Once it is moving, then it's a little bit less force. And if it's rolling, like a bike tire, it takes very little to overcome that friction force, which makes sense. If my bike is braking, and I'm trying to slide my bike on its wheels on the road, that kinetic friction force is going to be much greater than if the wheels are rolling. Much easier to just roll through. Or if it's sitting still and I'm trying to get it going in the first place, that'll be even more force. So rubber on concrete has a coefficient of friction of 1. Kinetic rubber on concrete, that would be like brakes, tires on the ground when you're braking, 0.8. And rolling friction force, 0.02. Look at the magnitude that that's smaller by. It's like 40 times less than the kinetic friction force. So this is 80%, and that's 40 times less. That's a lot. So the rolling friction force is smallest by a lot. Another note is that the kinetic friction force is the same regardless of the speed. So whether I'm pushing it at 1 mile an hour or 45 miles an hour, the kinetic friction force remains the same. Once it's going, it's the same to maintain the same speed. If I want to accelerate it, then that's going to change. But just to maintain a constant velocity, kinetic friction force remains the same. All right. Let's do a stop and think on that idea. So rank in order from largest to smallest the size of the friction forces, F sub A to F sub E, in the 5 different situations. 1 or more friction forces could be 0. The box and the floor are made of the same materials in all situations. Okay. So first, I have at rest with no push. Okay, if I'm not pushing on it, then there's no force of the push. So then there's no force of friction back on it. I'm pretty sure that this one's going to be 0. Right? There's no force, no push on it. Now I do have a push. It's on the verge of slipping. So this would be static, right? That's my static friction. It's not slipping yet. Pushing, speeding up. So this would be kinetic plus an acceleration, right? Kinetic plus acceleration in the positive direction. Constant speed, push. So that would be kinetic plus nothing. And then slowing down would be kinetic minus the acceleration, right? That would be kinetic plus the acceleration. Okay. So from largest to smallest, the largest is going to be the static friction force. The static friction force is really big. Just looking at my pieces here, remember static was much larger than kinetic. Static versus kinetic, static versus kinetic. It's somewhere between twice as much to 80%, 20% bigger. So it's quite a bit more. So I'm going to say that is going to be my number 1 is B, right? Then number 2 is going to be the kinetic friction force plus my acceleration, right? That one's going to be my 2. Constant speed is going to be my 3rd one because I'm maintaining just the kinetic. Now it's slowing down, so I've got kinetic minus the acceleration. I don't have to push quite as hard. That would be number 4. And then finally, this static one with no push, because there's no force, would be number 5. Okay. So I think that is going to be my answer. So I guess that means, see if I put it in order, F sub B is greater than F sub C, is greater than F sub D, is greater than F sub E, is greater than F sub A, which is equal to 0. Okay. Now the one thing that has me just a little bit wobbly is whether the speeding up kinetic plus an acceleration could be greater than the static friction force, like whether 1 or 2, because I wonder if I'm like really, really speeding up, like hundreds of miles an hour, then maybe that would require a lot. But I still think that my static would be the best. All right. Okie doke. Let's see, examples 511, 512, 513. I'm not going to do those for you, but they are good examples. They're found in the textbook for friction forces. So I recommend taking a look at those. They are on pages 140 and 141. So these are pages 140 to 141, all great examples. Each one goes through a different kind of scenario, and it helps thinking about like the vertical components and the horizontal components of the friction force. So with numbers, recommend. Okay, other kind of cool stuff. A microscopic view of friction. Okay, so we've been talking about friction as like this theoretical F sub K, F sub S, which is a weird way of thinking about it. We could actually think about what friction really is. Friction is molecules pushing against other molecules. So I want to move things across each other. Well, the ridges on the molecules are going to touch against each other and stop each other from sliding smoothly, right? The more ridgy they are, the harder it is to push past that, the more grippy it is. If I look at it molecularly, then I can see over here that I've got this ridgy surface of the floor. I've got this ridgy surface of the bottom of my tennis shoe. Those two surfaces contact. But the cool thing is to see so few points actually contact, because I've got the big ups and the big downs, and they're not like a puzzle piece. They don't fit together perfectly. Very few points actually contact. In fact, only about 1/10,000th of the surface area actually touches when you're touching something. That's pretty cool. And then if you want to get like super molecular and atomic, then nothing ever touches, because it's just the field of the electrons that aren't intersecting with each other, but that's going a little bit further. So you could say nothing ever touches anything, because the electrons just repel each other. There is no touch ever. The world is a sad and empty place with no touch. Oh. But for our purposes, on the kind of like semi-macro physics level, let's say 1/10,000th of the surface area touches. That's kind of cool. I like that. Even if I like put my hand fully on a tabletop, my hand is all the way on the tabletop, but my hand has ridges on it, even if they're microscopic ridges that I can't really see. Whoa, Mr. Williams, you have such wrinkly hands. Yeah, I always have. Since like I was a little kid, I've always had old man hands. Now I'm living into them. Just had to wait long enough to become an old man. All right, so another form of friction is drag. Drag is air resistance, and it's air resistance friction. So it always acts opposite velocity. Remember that friction works against the direction of motion. So the air resistance will work against the direction of velocity. And we can calculate drag if we make a few assumptions. So if we keep it in what I'm going to call the human scale, like within human realm. So if we assume that the diameter of an object is between a few millimeters and a few meters, so somewhere between like 2 millimeters and 5 meters. So that's like normal human size stuff. If we assume that the velocity of the object stays below a few hundred meters per second, so I'm throwing it out there as like less than 300 meters per second, that's really fast. That's like plane speed. So we're not going to be breaking the sound barrier, but as long as you're not breaking the sound barrier, you're probably safe there. If the object is in the air, like passing through Earth air, and it's near the surface of the Earth. Because remember, the higher you get, the less air is in the atmosphere, because gravity pulls the air closer to the surface. So the sea level has what we'll call the thickest air. And then top of Mount Everest would have really thin air because you're further up. So if you're near the surface of the Earth, then we can use this equation. All right. So this equation says that the drag, the force of drag, is equal to 1/4 times the density of air, and the density of air is 1.2 kilograms per meter cubed, per cubic meter, times the cross-sectional area of the object. So that could be a circle, it could be a square, It could be a rectangle. It could be a weird hand shape. You could use a variety of different equations to find the area, but you want to find the cross-sectional area that's touching the air. And then times the speed squared. So the big factor here is the speed, because the speed gets squared. So it's going to have the most impact, speed times speed again. The cross-sectional area is a big deal. And then obviously the density of the object, right? Density of air is much, much, much less dense than, say, density of water. If I was trying to find the drag due to water, it'd be a lot bigger because the water is much denser. Okay, so terminal speed is when drag is equal to the weight. So if I find the drag of the object and compare it to the weight of the object, if I drew a force diagram, I would have my force down is my weight. Initially, I would start with very little drag, right? Because I haven't started falling very fast. And so I'm just like hitting a little bit of air. And then the faster I fall, the more air I contact. And so my drag gets bigger and bigger and bigger and bigger until eventually it becomes the same as the weight. So right here, my drag is equal but opposite to my weight. And then it's reached terminal speed. It won't go any faster. The drag will never get greater than the weight, unless there's like an updraft on it or something, if you're sitting on a big fan underneath you. But then you'd be accelerating upwards. But generally, you don't accelerate upwards. You keep falling at the constant terminal velocity. So one kind of cool thing, there's a little example in the textbook showing that small animals have greater greater area to mass ratios. So they reach smaller terminal speeds because weight would have mass involved in it, right? Remember, weight is equal to mass times acceleration due to gravity. So that's where the mass comes in. Since smaller animals have smaller mass, but the same, like bigger surface areas, they tend to have greater area to mass ratios. So they reach smaller terminal speeds. So if you drop like an ant from a high height, it'll reach terminal velocity really fast. And then it generally doesn't hurt itself when it falls to the ground. It survives every time. The bigger animals, if you drop them from a high height, they could do a lot of damage when they land because they're reaching high terminal velocities, and then they could break a bone. Okay, so back up to the top. Let's do a real quick stop and think. The terminal speed of a styrofoam ball is 15 meters per second. Suppose a styrofoam ball is shot straight down with an initial speed of 30 meters per second. Which velocity graph is correct? Okay, so I know that it has to start at 30 meters per second, and all of these graphs do start at 30 meters per second, but the terminal velocity, terminal speed is 15. So I know it eventually has to get back to 15, right? It'll start at 30, but then it can't keep going at 30. It'll immediately slow down to 15. And then it'll kind of reach a level at negative 15, right? Negative 30 because I'm going down, negative 15 because I'm still going down, but I've reached terminal velocity. And it looks like that one is D. This starts at 30 and it shifts back, but then it keeps going all the way to 0, and it wouldn't just come to a stop, the styrofoam ball, unless it hit the ground. This one stays at 30 the whole time, so then the terminal, like you're just ignoring drag. This one gets faster. It can't get faster. It's already past its terminal velocity. And this one, same deal, passes 15 and then comes down to a stop. So I'm going to say this one shows that it reaches that limit of 15, but coming from the opposite direction. All right, let's do some sample problems. Objects in contact. So if I have two objects and those two objects are touching each other, like two cars that have already been in a rear end collision, right? They are connected to each other, big truck, little car, now they're stuck, and then one is pushing the other one, okay? They are in contact. When we're doing that, there are a few things to keep in mind for solving those problems. Number one, draw each object separately and prepare separate force identification diagrams for each object. So that would be like a picture of the truck, picture of the car, separate them, show the forces on each side. Once you've done that, draw a separate free body diagram for each object. So a free body diagram would be like my little set of arrows. So let's say this is going to be object A, this is going to be object B. I've got weight of B, normal force of B, weight of A, normal force of A, sorry, that should be a lowercase n, normal force of A. Then I've got the force on each one. So in this case, this force over here is the force of B on A. This would be the force of A on B, right? I always do it on the object that's getting the force on it, right? The force of A on B. And then I have this force, which is kind of, or actually, no, wait. I think I got those backwards. It doesn't matter. But I draw out all the forces showing which direction they're acting. I've done something wrong here. But then I have an extra force that would be like the force of the hand pushing on it. I've confused myself. Next, write Newton's second law in component form for each object. So component form is force of A is mass of A times acceleration of A. Force of B is mass of B times acceleration of B. And I might even have to break it down to force of B sub X, force of B sub Y. So then I'd end up with 4 force equations, the A, like the AX, AY, BX, BY. Then identify the action-reaction pairs of forces. If object A acts on B with force A on B, then B on A has to also be identified. And I know that they can be equal to each other. So the force of A on B will be equal to the force of B on A because they're equal and opposite pushing on each other. And then finally, if they are still in contact, they'll have the same acceleration. So I can set acceleration of A equal to acceleration of B. So then they all just become the acceleration, right? The regular acceleration. I can take out the subscripts and just say the acceleration is the acceleration if they're touching each other and moving in the same direction. All right, let's do a stop and think. Boxes P and Q are sliding to the right across, let's see, sliding to the right. There you go, I got my velocity arrow here. Across a frictionless surface. The hand is slowing them down. The mass of P is larger than the mass of Q. Okay, so this is bigger. Yeah, mass of P is larger than mass of Q. Rank in order from largest to smallest the horizontal forces on P, Q, and H. Whew. Okay, so it's slowing down. I'm going to start by drawing my force diagrams here. I have a force down, and that's going to be a weight. I have a force up, and that's going to be the normal force, and that's for P, P. For Q, I'm going to have a force down, which is weight, a force up, which is normal. Okay. Then I have the force of the hand on Q. The force of the hand on Q is going this way, that way, right? It's slowing it down. And then I also have the force of P on Q. Let's use blue instead. The force of P on Q. Zoom in a little bit. There you go. Is going that way. Now, because the hand is slowing it down, I know that the overall acceleration, so since it's slowing down, my acceleration has to be in that direction, right? It has to be going backwards. And that means my net force has to be going that way. Okay, so my acceleration is backwards, my net force is that way. That also means that the force of the hand has to be bigger, right? That has to be the force of the hand, so it's bigger than the force of P on Q. On P, the hand does not touch P, so there is no force of the hand on P. What I do have is I have the force of Q on P. And I know that has to be the same as the force of P on Q. Okay. So there, I have to have the force of Q on P. Okay, so Q on P and P on Q are equal, right? Those are equal to each other. The force of the hand is bigger because of the net acceleration, the net force slowing it down. Let me see if that helps. Okay. P on Q and Q on P are equal. Good. P on Q, Q on P are equal. P on Q, Q on P are equal. P on Q, no Q on P listed. Okay. Hand on Q, hand on P. No, there is no hand on P. That force doesn't exist, so D is out. Okay. Q on hand, hand on Q, Q on hand, hand on Q, Q on hand, hand on Q. Okay, those are all good. And then the question is just, are they equal to each other, less than, or greater than? So the force of the hand is greater than the force of Q on P. Force of hand, that one is greater, so that leaves me with B. Force of the hand is greater than the force of the boxes on each other. Whew. That is a tough one. Okay. Ropes and pulleys. For the last little section, I'm going to make this part 3, just because I am running out of time before class starts. So we're going to do ropes and pulleys in part 3. And I will see you then to talk about tension, ropes, and pulleys.